Your Holiness, it's a joy and honor to be here and speak to you about the philosophy of quantum mechanics, even though I'm sure it's a challenge for me because I know you know a lot about that. I've read your book, The Universe in a Single Atom. I know that you have met David Bohm, Anton Zeilinger, Carl Friedrich von Weizsäcker, and so you know a lot. But
usually I describe the hopeless student of quantum mechanics, quantum physics. I really seriously solicited lessons or explanation from late David Bohm.
Yes.
Few occasions. Then later, the von Weizsäcker, also is late von Weizsäcker.
Yes, that's right.
See, during I listen quantum physics, it seems I understand something. After finishing, nothing left. So your description is
So what you said about the understanding or not understanding quantum physics was quite true.
Okay. So we all have challenges here.
Yeah.
I think is the main thing. All of us.
So I hope it will be. It will not be worse with me. I hope. So the challenge will be to dig into the philosophy of quantum mechanics and to understand something very important about the difference between classical and quantum physics. You know that classical physics could
Michelle,
go on.
can you take the little bit? Yeah. Just a little away from your mouth. Yeah, that's good.
Classical physics could go on by supposing that bodies had an intrinsic existence, and some intrinsic properties such as mass or extension and so on. But in quantum physics, this idea that bodies have intrinsic existence and properties are intrinsically ascribed to the particles becomes a challenge. It becomes very difficult to sustain that at that point in quantum mechanics, even though certain physicists are still very eager to keep this old idea, this old absolutist idea of classical physics, they encounter so many difficulties that sometimes they renounce. So here I will insist on that, on the critique of the idea of intrinsic existence of bodies and of the idea that they have intrinsic properties. So to begin with, to illustrate this idea, I want to take a very simple example of how understanding of a certain situation can be improved largely by renouncing the idea of intrinsic properties. So my example comes from my own life. When I was a child, maybe I was 6, maybe I was 7 or 8, I don't remember, but I was riding a bicycle on the road in the night, and I was seeing the moon on my right, and also the line of trees. And a strange phenomenon occurred. When I was riding my bicycle, I saw that the moon was following me. And when I was stopping, I saw that the moon was stopping with me. And I was surprised. I thought, what's so special with me that the moon is following me? What's so special with the moon that it knows what I do? And so I was thinking about the intrinsic properties of the moon and of me that could explain that strange phenomenon. Then, when I was a little bit more grown up, when I was, say, 12 years old, I suddenly understood it had nothing to do with me or with the moon, but with the relation between me and the moon. The moon was very far away. Therefore, the angle under which I saw it changed very little when I was moving. Therefore, I had the impression that it was always with me. Whereas the trees were very close to me, and therefore the angle under which I saw them was going this way, and therefore I had the impression that they were going backwards. Therefore, I had the impression, I had the appearance of a moon following me, but it was not the case. There was so the whole explanation was clear to me as soon as I shifted from intrinsic properties to relations. I think this is something very important for science. Science as a whole, and especially physics, has done lots of progress when it was clear that one has to think in terms of relations rather than intrinsic properties. Let me give you an example. Now, not from my childhood, which is a little bit trivial. So let's think about Copernicus and its astronomy. You know that there was an amazing change between the astronomy of ancient times, the astronomy of Ptolemy, that was such that the sun was rotating around the Earth, and all the other planets were rotating around the Earth. Now, in this framework, how can you understand the apparent motion of planets on the starry sky? You see here the motion of Mars on the starry sky between August 2007 and I think August or April 2008, so 1 year. And you see on top, you see the planet Mars, which is going forward towards the left, then going backwards towards the right, and then going forward again towards the left.
Mars doesn't really make a full rotation.
Yes.
Okay, what
exactly.
you can see.
I'm speaking about what we can see on the sky, namely it's the appearance of Mars.
Oh, I see. Different position of world. That's right. Okay.
So now, to explain this strange phenomenon of Mars appearing to go sometimes forward, sometimes backward, sometimes forward again, Ptolemy invented an explanation which had to do with the intrinsic motion of Mars. So he ascribed to Mars an intrinsic motion which was made of two circles. Mars, according to him, was first rotating around the Earth by one circle, and then on that big circle around the Earth, there was what he called an epicycle, namely a little circle which was rotating also while Mars was rotating around the Earth. And therefore, as you see on the picture on the left, there were some loops, and these loops, when they are seen on the starry sky, appear this way, this strange going backwards and forward and backwards. So, according to Ptolemy, it was simple. You can explain that by a circle and an epicycle. Okay, but when he studied that a little bit further, he discovered that in order to account for the details of the motion of the apparent motion of Mars on the starry sky, he had to add not one epicycle, but a series of epicycles that had no end. So it was a problem. It was very artificial. Why 10 or 12 epicycles rather than 20? Nobody knew. So then came Copernicus in the 16th century, much later, maybe after 15 centuries. And he said, okay, let's suppose that in fact both the Earth and Mars rotate around the Sun. And suppose also that the Earth is rotating faster than Mars on its lower orbit, and Mars is going slower on its higher orbit. Then try to figure out what it is to be an astronomer on the Earth and look at Mars. And you will see that since Mars is going slowly, whereas the Earth is going quickly, we have the feeling that Mars is going backwards relative to us. And therefore, that explains why Mars looks like it is going backwards. It's not because intrinsically it is going backwards, but it's because the relation between us and mass is such that we are seeing it as if it were going backwards. So here again, this is a very important move. Science made a momentous step forward as soon as it understood that certain explanations have to be given in terms of relations rather than in terms of absolute properties. Now, quantum mechanics. What is quantum mechanics? I would say it's a generalization of this idea. Namely, you know, in classical physics, only certain properties were supposed to be relative to the observer. Only, say, velocity and position, nothing more. Mass was absolute, and other extension of bodies was absolute, and so on and so on. So only two types of properties were relative to the act of observation. Whereas in quantum mechanics, it's general. Any property whatsoever is relative to an act of observation. Spin is relative to an act of observation. Velocity, position, color of so-called color of particle, strangeness of particle, everything is relative to an act of observation. We say that all properties are replaced by or with observables. No longer properties, only observables, namely relational characteristics.
그래서 실질지도
돈 들어왔어요.
It's okay? Yeah. So, coming back to the wonderful saying of Richard Feynman that was quoted by John, he said, nobody understands quantum mechanics. Okay, and since Feynman was saying that, that was serious because he was the best American physicist ever and probably one of the best physicists in the world. So it was serious, but maybe he was wrong. I'm sorry. And maybe Bohr was right.
That's right. Neil Bohr.
Maybe Bohr. Well, because Bohr said, it's true that all these things seem so awkward, but maybe in order to make them, to transform them into something less strange, we have to change our very concept of understanding. And the idea which was behind this idea of Bohr was that we have to change the idea of understanding the world into an idea of understanding our relation with the world. And this was exactly what Niels Bohr said afterwards, when he said, we are both onlookers and actors in the great drama of existence. We cannot subtract ourselves. We cannot describe the world as it is in itself independently on us. We have to understand that we are actors in the drama of the world. Werner Heisenberg also said that. He said, quantum theory provides us not with an image of nature, but with an image of our relations with nature. As soon as you have understood that, and it's quite easy after all, many things in quantum mechanics become clear that were unclear before. So before that, I want to make a sort of pause at this point. Of course, you can complain. You can say, oh no, that's a regression. Classical physics was promising me a full picture of the world. And now quantum mechanics is no longer such a picture of the world. It's only a picture of my relation with the world, of our collective relation with the world. It looks like a regression. I want more. I want to go back to the good old time of quantum mechanics. And many physicists are like that. Even Einstein was like that, I must say. He said, no, I don't like quantum mechanics. It has so many strange features. I want to abandon it and to find a better theory which fits with the classical ideal. So obviously this standpoint cannot be dismissed easily because if Einstein had it, so it's a serious thing here again. Yet, if one accepts Bohr's and Heisenberg's point of view and try to go further in it, then something can change completely in our understanding. We can understand more we can make many paradoxes, so-called paradoxes of quantum mechanics, clearer. And this is what I want to do now. Show you that if we accept that all the characteristics that are dealt with in quantum mechanics are in fact understood in terms of relation between us and the micro environment, then many apparent paradoxes are less paradoxical. First example, the Schrödinger cat. I'm sure you know that very, very well. You have a picture of the Schrödinger cat experiment on the top right. The Schrödinger experiment is a box. Here you see also on the top, you see Schrödinger on the left and Bohr on the right, who are looking to the experiment. Now, the experiment is this one. You have a box, and inside the box, you have a big piece of radioactive material that has the probability 1/2 to disintegrate in 1 hour. Now, with the strange formalism of quantum mechanics, we say that during that hour, there is a superposition. In fact, the state of the piece of radioactive material is in a superposition between being disintegrated and not being disintegrated, just as what Arthur was explaining. Superposition. Both things are there at the same time. So in the same way as Arthur's photon, Arthur's photon was taking the two ways at the same time. Here, the radioactive material is, according to the description of quantum mechanics, I will come back to that later, what is the description in quantum mechanics. But at any rate, it describes in terms of a superposition, namely that it's both disintegrated and non-disintegrated during that hour. Okay, now let's go on. Then, if the atom, the piece of radioactive material disintegrates, then there is a counter that detects the disintegration. And suddenly it clicks. Then, when it clicks,
Radioactive.
it disintegrates. One atom of the radioactive material disintegrates and sends a photon or an electron to the detector. And the detector, when it receives this photon or electron, it clicks. Plop.
Yes.
And then it sends the signal that it has clicked to the computer, which is in the middle, which has these two eyes, you see. And then the computer has a hammer. It's a robot. It has a hammer, and if there is a signal that the radioactive material has clicked, it falls on the bottle and cracks the bottle. The bottle contains poison, and therefore, if the bottle is cracked, then the cat dies. Then a problem arises, the famous problem of Schrödinger's cat. Schrödinger is this man on the top left, you see. So Schrödinger's cat is here, and the problem is very serious because you remember that we have said that the radioactive material was in the superposition, half disintegrated, half non-disintegrated. Therefore, with this chain of events, the cat must be half dead and half alive, because if the radioactive material disintegrates, it's dead, and if it doesn't disintegrate, it remains alive. So apparently, and according to quantum mechanics, it should be half dead and half alive. But this sounds absurd, because when you open the box and see in the box, it's not the case. You see either a dead cat or a cat which is alive. So there is a paradox. What you could accept for an atom, you could hardly accept for a cat. What you could accept maybe that it was half disintegrated and half non-disintegrated, but how can you accept that a cat is half alive and half dead? There is a problem. This is the famous Schrödinger's cat paradox.
Can I just say, maybe we should add that there is no cruelty involved here because this is a thought experiment.
Exactly. Yeah. Thank you, John. Yes, this is perfectly right. And I must say, I've personally gone to Schrödinger's house, and I've seen that, in fact, Schrödinger was no longer alive. His house was in Alpbach, that you know very well, because you have been in conferences in Alpbach. In Austria. It is, his house is in
Oh, yes, so.
You remember that. And so I've seen in his house that he had many cats. And so he loved cats, in fact. So he,
Hopefully not experimented.
yes, unfortunately it's a thought experiment, yes, yes.
Experimenting on cats?
Never, never. So now we have a terrible paradox. We have our hairs that are, you know, I don't even know the word in English. They are
Stand up.
standing on our head. So what's the problem? But is there really a problem? Let's read the two sentences here. After Schrödinger preparation, the system atom plus cat is in a state of superposition. Namely, it's half alive and half dead. The state of the cat is half alive and half dead. On the other hand, there is another sentence here that says, one finds that the cat is either in the state alive or in the state dead. There seems to be a contradiction. One says that the state is half alive and half dead. The other says that it's either one or the other. Now, is there really a contradiction? I point out that without the word state, the two sentences would have no contradiction. If you understood this strange symbol as an expression of the information we have about the state of the cat, then there would be no contradiction. Because in one case, the information we have about the cat is incomplete. And in the other case, the information we have about the cat is more complete because we have opened the box and we have seen in it. And now we have full information. So, the so-called quantum state expresses nothing of the cat, but it expresses a state of information which has to do with the relation between us and the cat. This way, you perfectly understand that there is no contradiction, because the relation between us and the cat has changed when we have opened the door of the box and seen it. The very difficult point, the only difficult point in this case, is that, as Arthur said, it's not only a matter of contingent ignorance. There is no one watching outside with a sort of bird's eye view who would say, oh, in reality the cat is dead, or in reality the cat is alive. There is no possibility to do that. What we have is no absolute property of anything, but only relations between us and things. So only relations. As soon as you have understood that, you can understand that there are two different types of relations. One of partial ignorance and one of complete knowledge.
At least you see, our world, our sun, 5 billion of years.
Yes.
So at that time, no observer.
Yes, absolutely right. Yes, but now, who is saying
But
that?
fact is fact.
Yeah. Now, Holiness, who is saying now that the sun it has 5 billion years? That's the point. Even that science says that.
So in that case, we will have no criteria of distinguishing between what constitutes a true knowledge versus
Yes.
misknowing.
This is a very good objection, actually. Now, what is truth? Truth.
That's reality, Yamaroda.
That is.
Distortion, reality.
Yeah.
So we cannot make a distinction either, to push that line of thinking.
Yeah. We can do that. Well, why? Because
Then I think it's no need education, no need research this work.
we need to be very educated observers. We need,
educated
we need, for instance, when I say there is a glass, and Jimpa says, yes, there is a glass, and Chris says, oh, yes, there is a glass, and so on. There is a glass. Everybody agrees. This is intersubjective agreement. It doesn't need that there is something like intrinsic existence of the glass. We just need to have, we just need to agree about our relation between us and the glass. If we agree, perfect, we have intersubjective truth. We have intersubjective knowledge. We have, everybody can do something and agree that it works. Physics is an amazingly efficient tool for getting effects that everybody can observe and that everybody can agree upon. We don't need any absolute standpoint. We don't need what in philosophy in the West we call the God's eye point of view. That's the point. Now let's go on and push the logic of that. It may look strange, but it clarifies a lot. And then maybe we'll think about the philosophical consequences. Clarification 2, wave-corpuscle duality. Okay, it was very strange at the beginning of quantum mechanics to see that micro-objects...
How would you define it?
I mean, here it's wave-corpuscle duality without thinking that the wave property and the corpuscle property are intrinsic to micro-objects. Ontology means the science of being, what there is.
Nature of existence.
The nature of things.
Existence.
But here we don't speak of the nature of micro-objects, but about appearances once again. So let me come back to the history of this wave corpuscle duality.
So your line of thinking seems to be very much in tune with the Buddhist approach to all of these questions. For example, the very definition of what constitutes existence is something that is cognized by knowledge.
Absolutely.
And also what constitutes an object of existence, or it's sort of something that can be, something that is cognizable.
Yeah.
But
however, we do need to understand that that doesn't mean that the person who is looking at a particular glass, and if he turns his eyes away, the glass no longer exists. So we also need to find a way of avoiding that kind of consequence.
Of course, yes, of course. Well, yes, I don't want to go into such consequences, of course, but the problem is that, classical objects behave in such a way, in such a continuous and predictable way, that we have indeed the right to think that when we go out the room, the glass is still there. We have a right to do that because we know that it behaves in a very regular and predictable way. Whereas for micro-objects, it's not the case. They are behaving...
Yes, that's right, yes.
They are not behaving in such a way that we can say that everything goes as if it was going on even when we do not observe it. Something very different occurs when we do not observe it. For instance, effects of superposition occur, whereas when we do observe it, superposition collapses. So something is very different between observation and non-observation. Now, let me come back to wave-corpuscle duality. You know that in the history of quantum mechanics, wave-corpuscle duality was discovered essentially by Einstein about photons. And when Einstein discovered that, he was extremely puzzled. He says, it's impossible. And yet, God seems to have found a trick. Because it's real. It's impossible, yet real. So God, who made everything according to Judaism and Christianity, must have found a trick to stick these two very contradictory things together. Waves, which are extended, and corpuscle, which is a spot, a point, a dot. How is it possible that these two things are sticked on one another? How is it possible that a micro-object is both a wave and a corpuscle? But is it true that micro-objects are intrinsically waves and particles? The next steps of quantum mechanics have shown that it's not the case. In fact, if I had to say something in summary, I would say they are neither waves nor corpuscles. For instance, look at these effects on the left top. This is called a diffraction effect. This is the type of figure that is made by a set of electrons that are going through a little hole. And you see many circles. This is called a diffraction pattern, which is analogous to what we see on the bottom, which is an interference pattern. When we see an interference pattern like that, or a diffraction pattern, we say, oh, there is a wave, because usually waves do this type of pattern. But now, a wave gives diffraction and interference. But is it true, conversely, that any figure of any pattern of diffraction and interference means that there is a wave? Logically, it's untrue. A entails B, but B doesn't entail A. If A entails B, that doesn't mean that B entails A. This is one way. So it would be true that diffraction and interference proves the existence of waves if there were no alternative explanation for the existence of diffraction and interference than waves. And it's not the case. There are alternative explanations. There are physicists who found alternative explanations showing how you can get interference patterns or diffraction patterns without waves. Well, I can show it to you, but it's a little bit complicated. Now, conversely, you see tracks in Wilson.
Michel, am I right in translating that if it's a wave, it will necessarily show these patterns?
Yes.
But it's not the other way around?
Yes.
Okay.
Exactly that, yes. So also, the same thing holds for the idea that micro-objects are little bodies. You see tracks on Wilson chambers or on bubble chambers or any type of device like that. You see tracks. In sun, you have tracks. And therefore, you get the impression that here there are little bodies moving ahead and leaving the track in the chamber. Now, is it true that this is a proof of there being little bodies? The answer is no. Why? Because it would be a proof of that if there were no alternative explanation of these tracks. But in fact, some scientists, especially Erwin Schrödinger, who wrote the celebrated Schrödinger equation and who formulated the paradox of the cat, Schrödinger found such an alternative explanation without corpuscles. He can explain tracks without supposing corpuscles. It's wonderful. So that means that none of this proof is a proof of there being either waves or particles. Now, if we have understood that, that means that we are left with no idea of what is there, out there, in the micro world. What is there? Are there particles or waves, or none of them? We don't know. Now, when we are completely puzzled, we have to go back what we have, what we know. What do we know? We know only one thing. There are phenomena. There are spots on screens. There are clicks on encounters. There are tracks in Wilson chambers, things like that. Just that, phenomena. And then, from this phenomena, we can exert reason. We can use inference. And there was a theorem that was formulated a few years ago by two French physicists called Jean-Louis Détouche and Paulette Détouche-Février, who showed only by dealing with phenomena, nothing about what is particles or waves or anything, just phenomena. And they said a theory applying to phenomena that are relative to measurement contexts predict wave-like distributions of these phenomena. So it's very simple. If you accept that these phenomena can only be relational, namely express the relation between our measurement apparatus and the micro world, then you automatically yield the consequence that the phenomena are wave-like distributed. So they have appearance of waves, appearance only. So now we have the idea, very clear, which was already formulated by Bohr actually, that waves and corpuscles are nothing intrinsically existing or no intrinsic properties of micro-objects, but they are only relative to certain types of measurement apparatus we have. Certain apparatus will bring out wave-like effects, and certain apparatus will bring out particle-like effects. Now, let me go to another clarification. I hope it's clarifying, or maybe puzzling, but at any rate.
So what would rule out the possibility of explanation that, what would rule out the possibility of the following explanation that individual photons are corpuscular, and when you send them through the equipment, and then as a result of aggregation, it has this wave pattern.
Aggregation, that means many photons.
Many photons together.
I think
it is continuation.
Yeah, sort of,
one, because of that one photon, but it's continuation. The momentarily changing, the position change. So the very nature of that particle actually is changing.
The idea would be that the nature of the photon is changing.
The continuation is the
continuation. So couldn't one say that in a very discrete point in time, it may behave like a corpuscular, but if you take into account the continuum, it could behave like a wave. How would you rule that out?
Yes, it's a possibility. Actually, first of all, the collective effect cannot be involved just because the interference effect can be observed on one photon, completely isolated from anything. So first of all, it's not a collective effect.
Okay. But what about this idea of a single photon in its temporal continuum?
Namely changing sometimes as a corpuscle, sometimes as a wave. Yeah.
Yeah, but for example, it is moving.
Yeah.
So in a particular slice of time, it may be
So wave means is it like that movement?
Yes. Okay.
So and meantime, the particle itself also is momentarily changing.
Yes, I see.
Therefore, it is moving.
I see. I think there is only one model that fits your description and works quite well. It's the so-called bomb, double solution the hidden variable theory, the guiding wave theory. That's it. The guiding wave theory, which was formulated by De Broglie and by Bohm.
David Bohm,
exactly. Okay, so that he supposes that there is a particle which is guided by a field which has a wave-like property. And with that, he can explain a lot of things which are quite similar to quantum mechanics. Okay, so this is a model that fits a little bit what you say, and that works. That's a very important point, because when you propose an idea, you have to test it against all the facts that are predicted by quantum theory. And the only one theory which is a little bit similar to what you say and has already been tested against quantum theory is Bohm's guiding wave theory, on which you have one photon as if it were going. Oh, maybe I can show you the film more. No, I think it's too complicated. But at any rate, it's possible, but it's limited. It's limited to classical quantum mechanics, namely non-relativistic quantum mechanics. As soon as you go towards more complicated effects, such as quantum field theory, quantum chromodynamics, it no longer works. That's the reason why it tends to be abandoned. And why it's more, I think it gives a more coherent picture to assume, as I did, that there is no intrinsic properties or intrinsic nature, because this works throughout the whole spectrum of knowledge, of present-day knowledge, from ordinary quantum mechanics to quantum chromodynamics. So this is an argument. I don't say it's absolutely. So let me come to the fourth clarification, as I called it.
Yes.
For instance, you remember that Arthur has beautifully illustrated the idea that quantum particles are indistinguishable. And this is strange. How is it possible? Two bodies, solid bodies, that can penetrate into one another, disappear into one another, and suddenly reappear like that, as if they had lost their identity? It sounds strange once again. And you feel that there is something strange in the idea to ascribe such properties to solid bodies. Now, maybe there are no solid bodies, and this is the explanation. 슈뢰딩거 had exactly this idea. He said particles in the old naive sense do not exist. And modern physicists, such as Jos, the specialist of decoherence, said also exactly the same. Particles do not exist. This is the explanation of the difficulty of understanding this strange behavior of indistinguishability. Therefore, if they do not intrinsically exist,
Mrs. James got back. 2003 said what?
You have spelled it in French, particules. You meant particles.
Yes.
Sorry.
This is the French touch.
Oh, French English that's
Sorry.
Oh.
So yeah, that's right.
It's always wondering whether that has a special significance in this context of talking about things and their attributes.
That's right, yeah. Oh. Now, it's true that, okay, let's accept that they do not exist. Is it true that they do not exist in the absolute? Okay, maybe they just do not exist in the absolute, yet they have some mode of existence because we can spot them. There are counters, so they have a mode of existence. Okay? Now, in quantum fields, what mode of existence do they have if they do not have absolute existence? According to two of my French professors, I had two professors in my studies, Jean-Marc Lévy-Leblond and Bernard d'Espagna. And both of them have come to the same conclusion independently. They said particles have the mode of existence of a rainbow. Not of something solid, but of a rainbow. What is the mode of existence of a rainbow? It's a relational mode of existence. In order to produce a rainbow, you need three things. You need the sun, you need drops of water, and you need an observer. If there is no observer, there is no rainbow. There are photons everywhere, maybe, but not this wonderful circle if there is no observer or no photographic machine, actually, no camera. You need a camera or you need an observer in order to get a rainbow.